Guys, so this lesson, and we will be talking about the natural frequency. Okay, so what is natural frequency? And every object have a natural frequency. Okay, so say if you have a pendulum, right? The pendulum will have a frequency, and it just goes like that. And a bouncing mass will have a natural frequency as well. Okay, all right. So this lesson is actually really easy. So all we need to do is we need to know these two equations: t equals to 2 pi m over k, and then t equals to 2 pi L over G. And both of these two equations will be given to you, so you just need to use it, okay? And typically, if they tell you the length of the pendulum, it does not matter how big the mass is, you will know the period straight away. And once you know period, you use omega equals 2 pi over t. Then you will be able to calculate angular speed. And once you know the angular speed or angular frequency, then you can use all the equations you've learned before, okay? So for all these questions here, you see they will all be using this, okay? So that's pretty straightforward. So the only question I want to talk about is question 2 in your book. And this question is a little bit hard. Like you actually don't need to know this this question. Like this is a bit of a scholarship question, okay? So let's have a look. It says that a column of liquid have a mass, can oscillate in a U shape, okay? And then they talk about a lot of these things, and then what they did is they give you this. F equals to negative 2a rho gy, okay? So, well, this thing, okay, where A is this cross-section area, whatever, okay? Explain how this question shows that motion of the liquid is simple harmonic motion, okay? So, in any kind of question, you first you first define the thing. It's simple harmonic motion. What is simple harmonic motion? Simple harmonic motion is this type of motion. There are two criteria. One criteria is there is a force or acceleration, and that is going to be proportional to the displacement. Okay? And over here is a constant number. So force is proportional to y, to displacement, and acting in the negative direction. So you have a negative sign over here. So that shows this is going to be a simple harmonic motion. Okay. All right. And 2, we want to find out the period of the oscillation. Okay. So now I got this equation, right? So I want to find the period. So what we can do is we find how this is similar to what we've learned before, okay? So go match the equation we know, and which equation we can match? It's this equation. Acceleration equals to a negative omega, or negative omega squared y. Because this is our definition equation. So this equation also gives me a definition. So the differences over here is we have acceleration, and then over here is force. And that's not too hard. I can turn this into a force by multiply a mass to this side, and then multiply a mass to this side as well. So now this is going to be the same as this. So now this is going to be F. Okay, so this equation has turned into this equation now. Okay, now I can make these two equations together. I can go, well, negative 2a rho gy is going to equal to negative m omega squared y. In this way, I can cancel the y, cancel negative sign, cancel y, cancel negative sign, and I divide it to this side. Omega equals to m a rho g. Okay, give it a square root. Okay, so now it wants us to know the period, right? So we got omega. What is the relationship between omega and period? So omega equals to 2 pi over the period. So that is going to equal to this thing, square root a rho g divided by mass. So what is the period? Period equals to 2 pi square root m over a rho g. So that will be the answer. Okay, so these two equations actually come from exactly the same reason. If I can find the reason between the force and the y, and then I can use that to derive to get these two equations. Okay, but exactly why does it get this? Like what is the relationship? We don't need to know. So I'm just gonna not bother about it. I don't think you guys should bother about it either. So if you want, in your book, it actually explains it to you over here and then over the previous page notes. So they derived it for you, but you don't need to know that. All you need to know is just know that this and this equation to use. Okay, so yeah. Okay, so let's have a quick look of the first question over here as well. Say just so that you know how to calculate. Okay, so pendulum bob has a mass of 1.3. So let me take this away. Okay, pendulum bob has a mass of 1.3 kg. Okay, at this distance and equilibrium present release, swing 8 complete oscillation. 8 oscillation in 15.5 seconds. First, calculate the period. Okay, period, I know oscillation time. The period is the time taken for one oscillation. So I use 15.5 divided by 8. Okay, some people will get this wrong. So how you can remember is you're using second. The answer is going to be second. Okay, so then you get 15.5 divided by 8. That gives you 1.94 seconds. Okay, so that becomes your period. And then 2, the angular frequency. Okay, 2, the angular frequency, omega equals 2 pi over t. That 2 times 3.14 divided by 1.94. Okay, put that in the calculator. 2 times 3.14 divided by 1.94. Okay, 3.24 rad per second. Okay, and question C, calculate the length of the pendulum. The length of the pendulum tells you the period. So okay, t equals 2 pi square root L over G. Okay, and then put the time there, 1.94 equals 2 times 3.14 square root L divided by 9.8. Okay, so keep calculating. 1.94 divided by 2 divided by 3.14. That gives me 0.309. Okay, and then square L divided by 9.8 equals to 0.39 times 0.309 multiplied 0.309. Give me 0.095. Okay, and then L equals times 9.8, 0.94 meter. Okay, so that's the length. Okay, so explain what will happen to the period of the pendulum if the length of it is increased. Okay, if the length is increased, T equal to pi L over G. This is going to increase. It's on top over here, so period will increase. Right? Okay, and number E, explain what will happen to the period of the pendulum if the ball would release one that has twice the mass. Twice the mass, increasing the mass will not affect the period. Because in the equation, T equals to 2 pi L over G, we don't have the mass over here. So in this one, the mass bob will not change, okay? And it's kind of the same reason as like if we have different weight objects, something is light, something is heavy, and you release it, they drop on the ground at the same time. It's the same reason why the natural frequency is going to stay the same, okay? And I'm going to show you guys a really cool video talking about natural frequency, how we can change the length, and then it shows a really cool pattern so you can have a look, okay? All right, so that's it for today. Thank you for watching.